Hello students, in the last class we have studied relations. Till now in the topology paper we have studied set theory, functions and relations. All this was the logical foundation of our study of topology. Now in this today's class we are going to study the number system. Means mainly we are going to study integers and the real numbers, and this is the mathematical foundation of our study of topology. And also we will study the construction of the real number system, and for that we require the mathematical induction. But before going to that, we will begin with the definition of a binary operation on a set. So the definition of binary operation on a set is: a binary operation on a set capital A is a function f mapping A cross A into A, which means that if we have a function f, okay, if f is any function which is from the set A cross A means the Cartesian product of set A with itself, and if it is into the set A, then such function is called as a binary operation on set A, which means that a function whose domain is the Cartesian product of set A with itself and whose range set is the set A, then such function is called as a binary operation on set A. So we can check that on the set of integers the addition operation is a binary operation, because addition of any two integers is again a integer. Again in the set of integers multiplication is a binary operation, because the multiplication of any two integers is again a integer. On the set of integers, division is not a binary operation, because division of two integers may or may not be an integer. For example, 4 by 2 is an integer, but whereas 4 by 3 is not an integer. So like such, we have the definition of binary operation on a set. While dealing with a binary operation f on a set A, then instead of using our regular notation as image of a comma a dash under f, we denote by f of a comma a dash. So instead of using this symbol, we use the symbol as by denoting the function between the two coordinates of the point, such as image of a comma a dash. Now we will denote by the a f a dash. Okay, so like such is the notation, that is the change that you have to remember. Next, as we know that a and a dash are the elements of the set A, and f is a binary operation on the set A, means it is a function from A cross A to the set A. We use the plus symbol, multiplication symbol dot, as well as O, small o, and the asterisk. These symbols are generally used to denote the binary operation on a set. Next are the assumptions. We assume there exists a set capital R called the set of real numbers. Two binary operations plus and dot on R are called the addition and multiplication operations respectively, and an order relation less than on R such that the following properties hold. Which are the properties? The first we will study the algebraic properties, and the first algebraic property is that x plus y plus z is equal to the x plus y plus z. Second part of the first property is that x into y into z is equal to the x dot y dot z for all x, y, z in R, which means that the binary operation which is denoted by plus is associative for the elements of R, as well as the binary operation denoted by dot is also associative for the elements in R. Number second algebraic property is x plus y is equal to y plus x, and second part of the same one is x dot y is equal to y dot x for all x comma y in R, which means that the addition and multiplication, means the plus and dot, these two binary operations are commutative in the set capital R. Next, third property is there exists a unique element of R called 0, denoted by 0, such that x plus 0 is equal to x for all x belongs to R. This means that there exists a identity element under addition in R. Also again, there exists a unique element of R called 1, which is different from 0 and denoted by 1 such that x into 1 is equal to x for all x belongs to R, which means that there exists multiplicative identity which we denote by the 1 in the set capital R. So capital R has additive identity which is called the 0 element and multiplicative identity which is called the unit element. Next, number 4th property. For each x in R, there exists a unique y in R such that x plus y is equal to 0. And for each x in R different from 0, there exists a unique y in R such that x into y is equal to 1. So the properties covered in 4 are nothing but these are the existence of inverses. The first one is the existence of inverse under addition, and the second part is the existence of inverse under multiplication. But definitely in case of the multiplication, we have to consider the inverse elements of the non-zero elements of R only. Okay, inverses of non-zero elements of R under multiplication we have to consider. And number 5th, finally the last one, number 5th property is x into y plus z is equal to x into y plus x into z for all x, y, z belongs to R. And this is nothing but this is the interrelationship between the two properties, multiplication and division, which is the multiplication is distributive or addition. So like such we have the 5 properties. These are the algebraic properties. Now the next one is a mixed algebraic and order property. Only one mixed algebraic and order property, and that is the property number 6, which is if x greater than y, then x plus z is greater than y plus z. And if x greater than y and z greater than 0, then x into 0 is greater than y into 0. Okay, so this is the mixed algebraic order property. In this one we have used the algebraic properties of addition and multiplication, and the obviously order relationship is greater than, or also it is sometimes denoted by less than. So this is that mixed algebraic and order property. Now after this we have the order properties. So order properties are, really it is the 7th number property, which is the first order property, and it is the order relation less than has the least upper bound property. Means the less than operation, the order relation which we denote by the less than has the least upper bound property. And finally the number 8 is if x less than y, then there exists an element z such that x is less than z and z is less than y. X is less than z and z is less than y, which means that if x and y are any two different elements from the set A, then there exists some element z which lies in between x and y, which is to mean that between any two different members of the set R, there exist infinitely many members of the set R. So it is this 8th property. Next one. Now if you observe, all these properties are not new to us. We have already studied them in first year also we have studied, as well as in the second year, and in the 5th semester also we have dealt with these properties. Okay. Next one. From properties 1 to 5 follow the familiar law of algebra. Next, given x denotes minus x the number y such that x plus y is equal to 0. As we have seen in the algebra also, means in group theory as well as in ring theory, the inverse of x under addition we denote by the minus x. Okay, so inverse of x under addition is denoted by minus x, and it is called the negative of x. Similarly, the subtraction operation by the formula x minus z minus x is equal to the z plus of minus x, means the subtraction of two elements is defined in terms of the addition. Okay, as z minus x is nothing but it is z plus of minus s. So means x subtracted from z is same as addition of Z with the negative of x. Negative of x means additive inverse of x. Similarly, if x is not equal to 0, if x is non-zero element of the R, then we denote the multiplicative inverse of x by the symbol 1 by x. Okay, multiplicative inverse of x is denoted by 1 by x, provided that x must not be equal to 0 and that number y such that x into y is equal to 1, then obviously y is nothing but it is 1 by x, and it is called the reciprocal of x, multiplicative inverse of x or the reciprocal of x. Next, now the quotient z by x is given by the formula z by x is equal to the z into 1 by x. Okay, z by x is given by the formula z by x is equal to z into 1 by x. Next, now with the usual laws of sign and the rules of addition and multiplication of fractions, we have our regular laws that we have already discussed so many times in algebra especially. Next, the element x of the set R, we say that it is a positive if it is greater than 0, and we say that the element x of the set capital R is to be negative if x is less than 0. Next, the set of positive real numbers is denoted by the notation R plus. The set of positive real numbers is denoted by the notation R plus, and the set of non-negative real numbers, non-negative means positive as well as it includes the 0. Okay, so that set of non-negative real numbers we denote by the notation R plus bar. So clearly R plus is a subset of R plus bar, and R plus bar has exactly one member more than the set R plus, and that member is obviously 0. Next one, properties 1 to 6 are familiar properties in modern algebra. We have studied in the group theory as well as in ring theory. Properties 1 to 6, so many times we have studied those. Okay, and any set with two binary operations that satisfies properties 1 to 5 is called by the algebraicians as a field. Okay, so if we have the two binary operations and if these two binary operations satisfies properties from 1 to 5, then that set along with two binary operations is called as a field. Next, if the field has an order relation which satisfies sixth number property, if the field has an order relation that satisfies the property number 6, then it is called the order field. Then it is called as a ordered field. Next, properties 7 and 8 are the familiar properties of the topology. Property number 7 and 8 are the properties of topology, and they involve only the order relation, and any set with an order relation satisfying properties 7 and 8 is called by the topologist as a linear continuum. And if you remember, this definition of linear continuum we have already discussed in the semester 5th linear algebra paper. Now next we will define the set of positive integers, but before going to that, first of all we will define what is meant by the inductive set. See here, definition is a subset A of the set of real numbers is said to be inductive if it contains the number 1 and if for every x in A the number x plus 1 is also in A. See how we have defined the inductive set. A subset capital A of the set of real numbers. Set of real numbers is denoted by R and A is a subset of R. Then the set A is said to be inductive if it contains number 1. If it satisfies two properties, the first property is that it must contain the number 1, and the second property or the condition to be satisfied is if for every x in A the number x plus 1 is also in A. Means if x is some one member of the set A, then x plus 1 must also be in the set A. Okay, so these are the two properties. So if these two properties are satisfied by a subset of the set of real numbers, then that set A is called as a inductive set. Okay, next, now let us define the set of positive integers. Let capital A be the collection of all inductive subsets of R, then the set Z plus of positive integers is defined by the equation Z plus equal to the intersection of A over A belongs to the script A. See once again the definition. Let script A be the collection of all inductive subsets of R. Consider the collection of all inductive subsets of R. Then the set Z plus of positive integers is defined by the equation Z plus equal to intersection of capital A, where capital A belongs to the script A. Script A is the collection of inductive subsets of R. So like such, the set of positive integers is defined. Next, we note that the set R plus, means the set of positive real numbers, is inductive. Set of positive real numbers is inductive. Why? Because it contains 1 and it also contains 1 plus x, where x can be any positive real number. Okay. So obviously it contains 1, it contains 1 plus 1 2, it contains 1 plus 1 plus 1 means 2 plus 1, that is 3, it contains 3 plus 1 means 4, and so on, as well as it also contains 0.5, 0.5 plus 1 means 1.5, 1.5 plus 1 means 2.5, and so on. So therefore it is inductive. Next one, because it contains 1 and the statement x greater than 0 implies the statement x plus 1 greater than 0. Therefore Z plus, means the set of positive integers, is contained in R plus, set of positive real numbers. Therefore the elements of Z plus are positive. Okay, elements of Z plus means the positive integers are nothing but those are positive. Next one, also 1 is the smallest element of the set Z plus. 1 is the smallest element of the set Z plus. Okay. Next one. Now let us see some basic properties of Z plus, which follows directly from the definition of the Z plus. And the basic properties of Z plus are: number first, Z plus is inductive, means the set of positive integers is inductive. Number second, principle of induction. If capital A is an inductive set of positive integers, then A is equal to Z plus. This is the principle of induction. Next, we define the set Z of integers to be the set consisting of the positive integers, means Z plus elements of Z plus, then the number 0 and the negative of elements of Z plus. Negatives of elements of Z plus means additive inverses of elements of Z plus. Then obviously it is clear that the sum, difference and product of two integers are integers, as we have discussed in the beginning. Okay, addition means sum, difference and product of any two integers is always an integer, whereas the quotient of two integers may be or may not be an integer. That depends on those particular integers of which we are considering the quotient. So therefore the quotient of integers is not necessarily an integer, means it may be or may not be an integer. Next, the set Q of quotients of integers is called the set of rational numbers. See once again, the set capital Q of quotients of integers is called the set of rational numbers. Set of quotients of integers is called the set of rational numbers. There do not exist any integer a satisfying the condition that n is less than a is less than n plus 1. Means if n is any integer, then there do not exist any integer which lies between n and n plus 1, which means that n plus 1 is the immediate successor of n if we consider the set of integers, and similarly n is the immediate predecessor of n plus 1 in the set of integers. Next, if n is positive integer, then we use the symbol s suffix n to denote the set of all positive integers less than n. The set of all positive integers less than n is denoted by the notation Sn, and it is called a section of the positive integers. Okay, this set Sn is called the section of positive integers. Obviously then the set S1 will be empty. Why it is empty? Because it do not contain any positive integer less than 1. So the set S1 will be empty. Next one, the set Sn plus 1 denotes the set of positive integers between 1 and n. If you consider the set n plus 1, then it consists of all the positive integers lying between 1 and n, including both endpoints 1 and n. Therefore, like such is the set Sn plus 1. Sn plus 1 is the section of set of positive integers by the n plus 1 integer. Okay, section of set of positive integers by the number n plus 1. Next one, similarly we have obviously for the any positive integer n. So for instance, if we consider S4, it will consist of all the positive integers less than 4, means simply 1, 2, 3, and this is called the section of positive integers by the integer 4. Okay, S4 is the section of set of positive integers by the number 4. Similarly, if we consider S7, then S7 is the set of positive integers which are less than 7, and obviously that set will be 1, 2, 3, 4, 5 and 6, and clearly this is called the section of set of positive integers by the number 7. So like such we have the definitions. Next one is the well-ordering property. So the well-ordering property is every non-empty subset of Z plus has a smallest element. Every non-empty subset of Z plus has a smallest element. This is called as a well-ordering property. Let us prove this one well-ordering property. So proof is, we first prove that for each n belongs to Z plus, the following statement holds. Which statement? Every non-empty subset of the set containing 1, 2 up to n has a smallest element. Means we will consider if n is any positive integer, then the set consisting of positive integers between 1 and n, including both 1 and n, has a smallest element. First of all, we will prove that. So for that purpose, let A be the set of all positive integers n for which this statement holds. We are proving this by using the method of induction. Okay, so for that purpose we have considered that A is the set of all positive integers n for which this statement means which we are going to prove here, that every non-empty subset of the set 1, 2 up to n has the smallest element. This statement holds. Then A contains 1, set A contains 1. Okay, why? Because if n is equal to 1, then that set, this set will consist of only one element, and that element is simply 1, means it will become the singleton set. And obviously singleton set, that one has the smallest element. As it has only one element, its smallest element is the same that element. So this set contains the smallest element, which is 1 itself. Next, now then supposing A contains n, suppose set A contains n, where n is some positive integer, then we show that it contains n plus 1, means the method of induction we are using here. So let capital C be the non-empty subset of the set 1, 2 up to n plus 1. If C consists of the single element n plus 1, if C contains only one element and that element is suppose n plus 1, then that element is the smallest element of C. Okay, then that will be the smallest element of C. If not, otherwise means if not, then consider the set C intersection with the set 1, 2 up to n. Okay, if not, then consider the set C intersection with the set 1, 2 up to n, which is non-empty. Obviously this is non-empty because if n belongs to A, then this set has the smallest element, which will be automatically the smallest element of C also. Therefore A is inductive. Therefore the set A is inductive, and therefore we conclude that A is equal to Z plus. In that case we obtained that A is equal to Z plus, means the set of positive integers, and therefore our statement is true for every n belongs to the Z plus. Which statement? We have proved that every non-empty subset of the set 1, 2 up to n has the smallest element. That we have proved here by using the mathematical induction. Now next, now we will prove the theorem, and for proving that theorem, whatever we have proved just now, that we are going to use. So for that purpose, suppose that D is a non-empty subset of Z plus. Z plus means the set of positive integers. Okay, let D be any non-empty subset of positive integers. Then we choose an element n of D. Let n, small n, be any element of D. Then the set A, which is the intersection of D with the set 1, 2 up to n, is non-empty. The set A, which is the intersection of these two sets, is non-empty. Okay, then A has a smallest element K. Then obviously A will have the smallest element, and suppose that smallest element, for instance, is K. Then the element K is automatically the smallest element of the set D also. As the set A has the smallest element, which is K, which means that K is the smallest element of the common members of D and this set, and at this D is a subset of the set of positive integers. So therefore clearly K will be the smallest element of set D also, and therefore we have shown that if D is any non-empty subset of the set of positive integers, then it has the smallest element, and like such we have proved the well ordering property. Okay, so today we'll stop here and we'll continue in the next class. Thank you.